When I think about time, I often get thoughts about my past and the future. There is a difference in how we perceive time, how we live in the present, and how we have lived in the past, and how we will be living in the future. And we cannot reverse back the time. So, the distinction between past and future is at once a basic human experience. We were born in the past and we will die in the future. And in between, we witness innumerable happenings that are perceived by our mind in a way that, if considered in the reverse order, it will look absurd. Each of us grows and ages, but we cannot then turn back the hands of our internal clocks and reclaim the past. And so this in this podcast I will describe how the past and future are different and how we cannot go back in time. And this has a lot to do with entropy. Entropy is among the most confusing concepts in fundamental physics. And don't be scared of this word. Entropy simply means to describe everyday situations that have evolved from order to chaos, or simply from good to bad. Okay, so now imagine a bag full of, let's say, 100 coins, and you dump them on a table. If you found that all the coins are facing heads, you would be surely surprised. And that is a tough chance to land at. Getting that unique outcome is a tall order, or meaning it is a request that is very difficult to fulfill. Let's say you got one tail and other 99 are heads. The probability is that there are 100 ways that could happen. And when you keep increasing a tail outcome, the number of ways you can come up with that will give you the desired tails will increase. Suppose you got two tails and rest 98 are heads. The probability will increase to 4950 different ways to get that outcome. And as you increase it, say you want 50 tails and 50 heads, then the probability will be about 100 billion possible combinations. So instead of seeing each coin, whether it's a head or a tail, we consider them as a whole, like a group, and coins are members in that group. This is to make it a bit easy, and that is why you would be shocked if all the coins came heads, because there are billions and billions of combinations possible. So this is the essential concept of entropy. So for the rest of the podcast and to understand the past and the future, this is the basic meaning of entropy. So the more there are coins in the bag, the higher the entropy will be. A random shake is more likely to belong to a group with higher entropy, since such groups have more numbers or more members of coins. Here, numbers of coins are members, as I previously said. Think think of a messy room, and it will have high entropy because a great number of rearrangements of the things in the room will look the same. So if you put your bag and put it on another place, it will look the same. It will not change the state. The entropy will still be higher because the room is still disordered, or it's in a disordered state. And on the other side, a neat and well cleaned room will have low entropy because it is more structured and it is more in order. And this is same with the particles around us, or the particles that we are made of. So when you breathe in air in your room or anywhere, you don't care if it's oxygen, nitrogen, or any other gas that is going inside your body, but your lungs care. Your lungs just need the adequate amount of oxygen to meet your needs. And suppose for a large collection of molecules, a molecule is two atoms like O2, which is the oxygen that we breathe. And for a large collection of molecules in a container, we say that different configurations such as volume, pressure, and temperature pretty much looks the same. if they have the same volume, pressure, or temperature. So now let's take another example of a bathroom where you just took a hot shower and now the steam is everywhere in the bathroom. But the steam near the windows or near the shower curtain will have more volume, pressure, or temperature because there are less available space for the molecules to have rearrangement available. Conclusion is that smaller and tightly packed molecules have lower entropy and widely spread molecules have higher entropy because there are more configurations and more rearrangements possible. To summarize, having less molecules or less temperature or less pressure results in lower entropy, and more the molecules or temperature or pressure, higher will be the entropy of that particular system. But lower entropy state is very rare and it's unusual to have a lower state of entropy. Every time you step out of the shower, entropy will be higher. The more longer the shower, the higher the entropy gets because there will be more molecules accumulating in your bathroom. And if you encounter low entropy states, it cries out for explanation, such as an egg and such as the anthill or the mug each rise from particular form of life arranging its random configuration of particles in the environment to yield orderly structures. Entropy is focused in the second law of thermodynamics, which focuses on growth. So this law says that over time there is a tendency of entropy to increase. If a system, let's say you bake something in an oven, that is the low entropy state because it's raw, and as the time passes the aroma of the food will disperse, resulting in the higher entropy state, and no one can stop it. Now that the entropy is clear, let's talk about the universe, which is the good part. So the probability of getting raw cooked food from a fully cooked meal is closer to zero. The laws of physics put the future and past on equal footing. So therefore entropy can decrease, but it's very unlikely. So entropy is overwhelmingly likely to increase. Our observation of distinction between the past and the future exists because of our consciousness and because there are happenings around us, that is, work is done. Today, then the entropy of the universe is high and is increasing every day. And from the second law, when we derive the state of yesterday, we get lower entropy. And as we yield the trail of ever decreasing entropy, it takes us to the Big Bang. So the Big Bang is a highly ordered, exceedingly low entropy starting. From the point of the Big Bang is why today's universe has a higher entropy, allowing us for an eventful future that differs from the past. And without an environment full of low entropy at the beginning, or for example, take example of our body, which is highly low entropic when we are born, or even at the molecular level, we humans would not be here to notice this. And entropy has a lot to do with heat. So let's talk about heat. And so when you touch a hot saucepan, you'll say the heat flowed from the pan to your hand. But does heat really flow? That's the question. And earlier, this was believed that heat is flow, but it's not. The molecules that are very rapidly moving in the saucepan creates warmth, and when you touch the pan, the molecules in your hand starts to speed up, and this moving of molecules in your hand is what we call warmth. Correspondingly, the slower speed of molecules in the pan means temperature is decreased. This is what we meant by the flow of heat. What flows is not a substance. The molecules in the pan stays in the pan, The molecules in your hand stays in your hand. What flows is information. This same applies to entropy. As soon as there is heat, the future is different from the past. The fundamental phenomenon that distinguishes the future from the past is the fact that heat passes from the things that are hotter to the things that are colder. So, entropy lies at the heart of how a universe heading towards ever greater disorder can nevertheless yield and support ordered structures like stars, planets, and people. And this is the reason why entropy is very important in the evolution of the universe and evolution of us. And so in the next episode I will head back to the Big Bang and will describe how entropy is related to our origins. Until then, goodbye. And also, if you like this podcast and if you like this episode, then do share it with your friends, family, or colleagues, and subscribe this podcast too.